Hello and welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be covering our second honors topic, and that is equilibrium constants. Our aim for today is, how can we use equilibrium constants to determine in which direction a reaction is favored? An equilibrium constant, or KEQ, capital K, subscript EQ, is the ratio of product concentrations to reactant concentrations at equilibrium, with each concentration raised to a power equal to the number of moles of that substance in a balanced equation. Here we have an example of a chemical reaction as it reaches equilibrium. We start off with only reactant, N2O4. As the reaction proceeds and as we reach equilibrium, that turns into the product, it decomposes into the product NO2 in a decomposition reaction. So here on the left graph, we have a concentration versus time graph. We start off with only reactant, only N2O4. There's no product yet at the beginning. There's no NO2. As the reaction progresses, the amount of reactant, the amount of N2O4, decreases. At the same time, the amount of product, NO2, starts at 0 concentration, and as the reaction proceeds, the amount of NO2 increases until equilibrium is achieved. For concentration, when equilibrium is achieved, the concentrations remain constant. That's why you see this flat line. Remember from the last lesson, when equilibrium is reached in a chemical reaction, you have con. The rates, RE, of the forward and reverse reaction are equal, while the concentrations remain constant. Rates are equal of the forward and reverse reaction. Concentrations of reactant and product are constant. So let's talk about the rates. Here we start off with the rate of the forward reaction, N2O4. As time goes on, the rate of the forward reaction is going to decrease. And we start off with the reverse reaction, NO2, at 0. As time goes on, the rate of the reverse reaction will increase. So the forward reaction is represented by this blue, and the reverse reaction is represented by this red. Once again, the forward reaction as time goes on decreases, and the rate of the reverse reaction increases until the rate of the forward and reverse reactions are equal. We reach equilibrium when the rates of the forward and reverse reaction are equal and the concentrations remain constant. Here is the equilibrium constant formula. But before we look at the formula, let's take a look at this example reaction. We have A plus B, capital A plus capital B, goes to double arrows, so we know we're at equilibrium, goes to capital C plus capital D. The capital letters represent the substances. Whereas the lowercase letters, lowercase a, lowercase b, lowercase c, and lowercase d, in front of the substances, represent the coefficients. So the lowercase letters represent the number of moles of each substance in a balanced chemical equation. Now let's take a look at our KEQ formula. We have in brackets capital C raised to the lowercase c power times in brackets capital D raised to the lowercase d power divided by, in brackets, capital A raised to the lowercase a power, times, in brackets, uppercase B raised to the lowercase b power. Now we notice on the top we have the products. So we have products over capital A and capital B over the reactants. So product 1 times product 2 divided by reactant 1 times reactant 2. The brackets represent concentration or amount. Could be in moles or molarity. We'll take a look at that when we do some practice problems. This is an important note. The exponents in the equilibrium constant expression are the coefficients in the balanced chemical equation. So we have C raised to the coefficient, the number of moles for C, times D raised to the lowercase d, the coefficient, the number of moles of D. Same thing for A and same thing for B. You'll see this make a little bit more sense when we start doing practice problems. But first, I have a couple notes about KEQ equations. So, we have an equation. Obviously, we're going to do some calculations today. Some notes first. When we do our calculation, if we get a value of KEQ, our answer, when we hit enter for the final time in our calculator, if that number is greater than 1, that means the products are favored over the reactants. In summary, a KEQ greater than 1, greater than the number 1, means that the forward reaction is favored. The forward reaction is favored. You could also say that the products are favored if the KEQ value is greater than 1. The opposite is true as well. A KEQ value of less than 1 means that the reactants are favored over the products. So a KEQ, in summary, a KEQ less than 1, the reactants are favored at equilibrium, which means the reverse reaction is favored. This is an important note as well. When we're setting up these equations, solids and liquids do not factor into these equilibrium constant expressions. We only worry about gases and aqueous solutions. Do not include solids and liquids in your calculations. Only gases and aqueous solutions. Let's do practice problem number 1 together. Practice problem number 1 states the colorless gas dinitrogen tetroxide N2O4 and the dark brown gas nitrogen dioxide NO2 exist in equilibrium with each other. Here's the equation. N2O4 gas, as at equilibrium, goes to 2 moles of NO2 gas. A liter of gas mixture at equilibrium at 10 degrees Celsius contains 0.005 moles of N2O4 and 0.030 moles of NO2. Write the expression for the equilibrium constant and calculate the equilibrium constant KEQ for the reaction. Well, let's start off first by writing down our original equation. KEQ equals products, concentration of products over reactants. So for this one, our products are NO2 and our reactants are N2O4. However, our products have a coefficient of 2. So when we rewrite this, KEQ, and we put NO2 in brackets, we must raise that to the second power. Whereas the reactant N2O4 does not have a number in front of it, so therefore it's going to have an imaginary number 1. We don't have to write that as a exponent, because anything raised to the first power is just itself. Now let's plug in some numbers. We have N2O4, we have 0.005 moles. And we have 0.030 moles of NO2. Remember, we raised that to the second power. So when we punch that into our calculators, we should take this one step at a time. We should take the 0.030, raise that, the caret, so we should punch in 0.030, raise that caret to the second power, hit enter. We should get 0.0009 divided by 0.005 and hit enter again. Don't clear out your calculator. When we do our calculations, the moles cancel out. KEQ is not going to have a unit. It's going to be a naked number. So when I divide these two numbers, I get 0.18 is my KEQ, which means this number, since it's less than 1, it's going to favor the reactants. So the reactants are favored, or you could say the reverse reaction is favored. Let's try problem number 2 together as well. Practice problem number 2 states, the reversible reaction below produces ammonia, which is a fertilizer. At equilibrium, a 1-liter flask contains 0.15 moles of H2, 0.24 moles of N2, and 0.10 moles of NH3. Calculate the KEQ for the reaction. Once again, remember, KEQ equals the concentration of products divided by the concentration of reactants. The brackets mean concentration. So when we rewrite this equation, KEQ, we have our products, our NH3. We look to see if there's any coefficients. There are, so we're going to raise that to the second power, divided by our reactants. We have N2, which does not have a coefficient, so it has an imaginary 1, which means we don't have to write the coefficient. Once again, anything raised to the first power is just the same number, times H2. We look to see if H2 has any coefficients. It does, so we're going to raise that to the third power. Let's plug in some numbers. So we have for NH3, we have 0.10 moles of NH3. We're going to raise it to the second power. Divided by N2. So we have 0.24 moles of N2 raised to the first power. And finally, we have 0.15 moles of H2 raised to the third power. I would once again be very careful when I punch this in. I would do 0.10 raised to the second power, which of course gives me 0.01 moles over 0.24 moles times 0.15 moles raised to the third power, which gives me 0.00081 moles. The moles and moles cancel out. Our KEQ does not have a unit, of course. So let's do 0.01 divided by 0.00081. And our KEQ is going to equal 12.3456791. If we were to do significant figures, 2, 2, and 2. So our KEQ, rounded to two significant figures, 3 is lower than 5. So our KEQ is going to equal a value of 12 for problem number 2. 12, obviously it is higher than 1. It's greater than 1. So we say our products are favored. Or this reaction favors the forward reaction. So the reaction is favored as written. It would go forward with that KEQ value greater than 1 of 12. Let's do one more problem together. Problem number 4 states, at equilibrium, at 100 degrees Celsius, a 2.0 liter flask contains 0.05 moles of PCl5, 0.050 moles of H2O, 0.750 moles of HCl, 0.500 moles of POCl3. Calculate the KEQ for the reaction. Once again, KEQ is equal to the concentration of products divided by the concentration of reactants. When we look at this problem, we don't have all gases this time. H2O is a gas, HCl is a gas, and POCl3 is also a gas. However, PCl5 is a solid. We do not consider solids or liquids when performing KEQ equations. So PCl5 will not factor in our equation. So now we can rewrite. KEQ is equal to the products, HCl. Let's check for coefficients. It has a coefficient of 2, so raised to the second power, times the other reactant, POCl3, which does not have a coefficient, so we don't have to put anything, or we could put the number 1, over One more time, we only worry about the gases or aqueous solutions, not solids, not liquids. So we're only going to write H2O for the reactants. And since there are no coefficients, we could either put the number 1 or we could just leave it alone. Now we plug in numbers. Be very careful when solving these problems. Make sure you have the right numbers corresponding to the correct substances. So we start off with HCl. We have 0.750 moles of HCl raised to, once again, the second power, times POCl3. So we have a half mole of POCl3, 0.500 moles, over H2O, we have 0.050. Once again, raised to the first power. I would take this very slow again. I would do 0.750 raised to the second power times 0.500. I would hit enter, and I would get an answer of 0.28125 moles divided by 0.050 moles. The moles and moles cancel out. So when I divide by 0.050 moles, I get KEQ is equal to 5.625. If I were to round to significant figures, I see 2, 3, 3. So my final answer will have 2 significant figures, the least amount of significant figures. So my final answer, since 2 is less than 5, I round down. My KEQ is going to be 5.6. We have to decide what is favored in this reaction, the reactants or the products. Since 5.6 is a value greater than 1, the products are favored. Or you can say the forward reaction is favored. This favors the forward reaction. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we looked at calculating equilibrium constants. First, we looked at 2 graphs, a concentration versus time graph, and then we looked at a reaction rate versus time graph. Remember re-con-con. For a reaction at equilibrium, the rates of the forward and reverse reaction are equal, and the concentrations of the reactants and products remain constant. Then we took a look at calculating equilibrium constants. Remember, to calculate equilibrium constants, KEQ equals the products over the reactants. And don't forget to raise the amount of each substance to its appropriate coefficient. Finally, we looked at the answer, we looked at the KEQ value, and if the KEQ value was greater than 1, we said that the forward reaction was favored. A KEQ greater than 1 favors the products, whereas a KEQ less than 1 favors the reactants. A KEQ of less than 1 favors the reverse reaction. Thank you again for joining us. I hope you learned something today. Please join us again soon.